Hello folks, welcome back. I have received the CCD chip and gotten it set up. Stuck on a breadboard. We've got a couple of voltage regulators for 9 volt and 5 volt power supply to the CCD. We're getting power from a 12 volt wall wart, and we've got the Blackpill on the other side of the board, and then underneath the connector to the Blackpill is the OR chip that is taking the 3.3 volt signals out of the Blackpill and sending them into the CCD. And then you can see the little probes from my logic analyzer plugged in. It turns out that logic analyzer, we can switch the input lines from just sensing logic to actually sensing sampling a voltage. And so it's kind of like an oscilloscope or a mixed signal oscilloscope. You can sample digital and discrete analog values. Anyway, so you see the yellow wire lying over the face of the CCD here. When we sample, and we can see this is the dummy pixels at the beginning of the row, and then this sort of little bump here is the shadow of the wire. And so that's working. The electronics part of it is working. This is the same pulse chains that we were generating before are still there, and you can see that once you zoom in enough, this is discrete samples, not a continuous line like would be on an oscilloscope. Digital oscilloscopes, it's discrete samples, but they're a lot closer together as well. I forget, this is 10 million samples per second here. So this is a 1 megahertz signal, so there should be 10 dots across that 1 megahertz. Anyway, so that's pretty cool. I like that a lot. It's nice. I can just have it on my desk for troubleshooting. All right, so the next piece, we need to be able to get the data into the ADC and out to the computer. So to change the configuration for our driver chip, we need to change the ADC from looking at the internal temperature sensor to looking at an external pin, and you can see I've already changed this. So we had it pointing at the temperature sensor. Now it's looking at pin 1, PA1. And then the other thing we need to change is when I wired the chips up on the breadboard, I got timer 3 and timer 4 mixed up. So that's the reset gate pulse and the extended clock pulse for reset. And so rather than taking apart the breadboard, I just switched where the timers were. So that's got you caught up to where we are now. The next thing that we need to do is, if you recall on where we had left it after implementing the virtual COM port over the USB, it was just sending data back over the USB. Whenever we hit a button, it would send some data. So we tell it, send me some data, and it would send the data, which is great. But we need to actually start the ADC conversion process at the same time that we reset the CCD. In other words, we need to get our ADC running in sync with all those other pulses, so that when we do our conversion, we're actually converting the period of data coming off of the ADC that we're interested in. And the way we're going to do that is to cause one of our reset pulses to generate an interrupt, and then we'll write an interrupt service routine to get the ADC get started. So here's how we get that set up. We go into timer 3, and there's this NVIC, something interrupt controller, virtual interrupt control. I don't remember what NVIC means, but you need to enable this timer 3 global interrupt. And you would think that that would be all you needed to. Well, you need to then go into main, and up here where timer 3 was starting in one pulse, you have to add the start IT to tell it to start one pulse with an interrupt. And that should be all you have to do, except that it's not, because the code generator does not actually enable the interrupt. So if you look in the oh, this isn't where I want to look. If you look in the timer initialization for time 3, it goes through here, does the setup just like we expect, but it should somewhere in here be enabling the interrupt, and it doesn't do that. So to enable the interrupt, I have found this little snippet of code, and this was after an extended period of searching around on the internet trying to figure out why this interrupt wasn't firing. And yeah, so this is how you enable it. It's underscore HAL time clear interrupt, and then you give it the handle to timer 3, and the specific interrupt that you want to make sure is cleared is timer interrupt update. So there are a whole bunch of possible interrupt conditions that you can set for these timers, including output compare. And I mean, the way that I found out about this, it was digging through the code. And so the update interrupt happens when the one pulse timer gets to the end of the pulse and stops. That's when that update interrupt gets sent out. And so we're going to clear it to make sure there's not one already there, and then enable it. And once we do that, then we need to go down to the bottom of the main C file in this user code begin 4, and we need to put in the callbacks. And there's a callback for period HAL timer period elapsed callback. And again, digging through the code to find where this definition is, but we're going to tell it, if it gets called, we're going to look and make sure that it was called for timer 3, which is what we're expecting. And then once we get to here, we're going to say we're going to start the DMA process if we have enabled a flag to say start the ADC. And the reason is we don't want to start it every time we get to a reset pulse. We only want to start it when we actually want to copy a bunch of data from the CCD into memory. So it says if that enable flag is set, then start the DMA and clear the enable flag, and then otherwise don't do anything. And then there's a second callback that you don't have to set up the interrupt for. It just gets called when the analog to digital conversion is completed. And this gets called at the end of the complete row of, like, we gave it a buffer to fill and using the DMA, and so this gets called when that buffer is full. And so at that point we set an ADC complete flag and then go back to doing whatever the computer was doing. So these interrupt service routines shouldn't be doing anything complicated. Like, we wouldn't want to start sending over the USB from in here, because this is blocking everything else from running until it returns. So we have to add these two interrupt service routines, and then up in our while loop, way up here, we're going to say if starting up here, we're going to create that enable flag, create the complete flag, and then down in the initialization code, we're going to say enable the ADC and also set the complete flag to 0, cleared. So it's not complete, and then the next time that we go through that interrupt service routine for the reset pulse, it should start the ADC. So once we get all these timers initialized and get them started, once this one starts and starts generating interrupts, it should fire up the ADC. We're going to give one more poke at the ADC right here, just because it seems to doing that makes it work right. And I'm not completely sure why. And then we drop into our while loop and we say if the ADC is not enabled, so it is gone through and finished, and the ADC complete flag is set, then we sit there and we check if somebody has asked for some data. If they ask for some data, then we send it, and at the end of sending it, we're going to clear the ADC completed flag and set the enabled flag again. And so then it'll go out and fill the buffer up with data and be ready to send again when we get back to the top of this while loop. Or we may come through this while loop a bunch more times before all of this completes, but that's how we set up the synchronization. And if we do that, we should be getting data. And so the way to look at the data is I just used a pretty simple Python script. And so this is 50 line, not even, 48 line piece of Python. We're going to use the PySerial library for managing the serial port, and we're going to use matplotlib for drawing our data out in a graph. So the first thing we need to do is I wrote a little function to get the information off of the serial port and into memory, or into the Python memory, so we can graph it. And just stepping through this function, we're going to reset the input buffer so that if there's any hanging bytes that didn't get read before it finished last time, we get rid of them. And then we're going to say send us new data, and then create a couple local variables to put the data in, read in a line of data 2 bytes at a time, convert those bytes from 8-bit integers into a single 16-bit integer, pretty convenient little conversion that lets you specify the byte order and tell it that it's not signed. And then we're going to subtract, just so that you saw on the trace from the logic analyzer that the dark is high voltage and the illuminated portions of the CCD drop down in voltage. And so in order to flip that around, we know that it's 12-bit data, which is 4096 possible values. And so we're just going to subtract everything from 4096 in our code. And that gives us the bright areas being high and the dark areas being low, which just makes it easier to understand when we look at it. That's what this 4096 minus the red in value. And then we stick it together into an array and return it. And then this is opening the serial port for reading and writing. And then there's about, 1, 2, 3, 4, 5, 6, 7, 8, and another 4. So 12 lines, 14 lines of Python code to get the plotting library drawing a graph for us. And when we do that, we got a nice little real-time graph of the output of our CCD. So that little yellow wire you saw, now I'm going to move it around and you can just see it moving around in real time. It's pretty neat. So at that point, we've got a functioning driver for the CCD. It can be tidied up some, and we don't really have a GUI yet, although this plotlib is just really cool for having a built-in GUI, so we can zoom in on a piece of the plot and see what's going on. That's pretty cool. And back to the way it was at the beginning, and yeah. Anyway, I think I will leave it at that point. I will, if anybody is interested in the code, drop me a comment and I'll put it up on GitHub or something. It doesn't seem like it's all that interesting to a lot of people, but knowing how to get that the one pulse mode generating an interrupt, that was just a bear to find, and so I wanted to share that little bit of the process. That is, where is it? It's here in timer 3 init. The key bits were this HAL time clear interrupt, timer 3, and then the update interrupt. So if you're trying to do something similar, I hope that helps. And I guess I'll leave this here for now.